Hey guys, today we're going to talk about logarithmic differentiation. We use this method when we need to simplify a complex exponent given in the problem statement. For example, x squared plus 1 to the power of e to the x. A quick rundown of the steps we need to do here is first, take the natural log of the entire problem statement, y equals x squared plus 1 to the power of e to the x. Second, take the derivative of that natural log of y, and then third, plug in y back into the solution, because you'll see in a second here that we will get our answer with the y term remaining. So we'll just need to plug that back in. For our final answer. So let's apply the first step here and apply the natural log to the entire problem statement. We have ln of y equals ln of x squared plus 1 to the power of e to the x. Followed by the second step, which is going to be taking the derivative of the entire statement we just wrote out. So taking the derivative of ln y equals the derivative of ln of x squared plus 1 to the power of e to the x. We can simplify that a bit here by just simplifying the left-hand side first. So we have the derivative of ln y is 1 over y times dy dx. And then the derivative of a little more complicated, but this is the beauty of log differentiation, is we could just use the rule ln of a to the power of b is just b ln a. So we can rewrite the right-hand side actually as the derivative of e to the x times ln of x squared plus 1. And this is a much easier statement to take the derivative of through using the product rule. So let's apply the product rule over here on the right-hand side. To take the derivative of e to the x times ln of x squared plus 1, we're going to first define u as e to the x. Then we're going to define v as ln of x squared plus 1. So continuing the product rule here, we derive u, du dx is e to the x. And dv dx is a little bit trickier. Since this is a composite function, we're going to need to apply the chain rule here. And you can go back in the playlist to this video if you need more chain rule examples. But for this video, let's just jump right in and start defining how we can derive ln of x squared plus 1 using the chain rule. So first step here, let's define u as the inside part of the function, which is x squared plus 1. The outside f of u is going to be ln of u. Then du is 2x, and f prime of u is just 1 over u. So to get this derivative here, we need to multiply du times f prime of u, which is 2x times 1 over u, but we'll plug u in right here as x squared plus 1. So when we multiply these two together, we're left with 2x over x squared plus 1. And this is going to be the derivative to plug into our product rule work up here. Okay, so let's finish out our derivative of the original e to the x times ln of x squared plus 1, which is the right-hand side of our equation in blue. And the product rule formula is as follows. So it's u times dv dx, which is e to the x 2x over x squared plus 1, plus du dx times v, which is e to the x again times ln of x squared plus 1. And that sum is the complete derivative of the right-hand side of our equation. So we can plug this in on the left in blue here and take it to step 3 of log differentiation, which is plugging y back in. So let's rewrite this all. Now that it's all rewritten, we notice that we want to isolate this dy dx to get our final solution. So we just multiply the whole thing by y. But keep in mind, we're not allowed to keep a y term in our solution. This y is actually referring back to what's given to us in the problem statement, which is y equals x squared plus 1 to the power of e to the x. So we actually need to substitute this into our solution to get our final answer. So all that being said, we're left with dy dx equals e to the x 2x over x squared plus 1 plus e to the x ln x squared plus 1, all multiplied by our problem statement y, which is x squared plus 1 to the power of e to the x. And finally, that's going to be our answer to this problem. So as you can see, the use of the rule ln of a to the power of b equals b ln a is the entire beauty behind this method. And you only want to use this method if you have a complex exponent in the statement you're given to take the derivative of. So that wraps up this video. I have another log differentiation example linked here in the playlist. But again, guys, I think this type of problem is perfect for differentiating you against your classmates on the exam, because people fail calculus exams all the time because they don't know their algebra. Just please keep your work organized and go through the steps without making any simple algebraic mistakes, and I guarantee you'll be able to do great on the exam.